Welcome back, Physical Science 20. This is the third video for the wave properties section. So with this, we're just going to look at a few questions here using the equations, the wave equations that we've looked at, and seeing how that all comes together. So number 15, a sound wave produced by a clock chime is heard 515 meters away 1.5 seconds later. So based on these measurements, what's the speed? The sound wave has a frequency of this, what's the period, and then what is the wavelength? So we're given distance and time, we're asked to find speed, so quite easily done there, folks. We know, and what this really helps, if you write down what information you're given in the question, that helps you sort it out, and then from there figure which variable we're looking for. This first one we're looking for speed, so V is equal to D over T, 515 divided by 1.50, 346 meters per second. Okay, and if we know we're looking, we have the frequency, what's the period? Frequency, what's the period? We know frequency, what's the period? So there, you're going to use that relationship there. So T is equal to 1 over F. F is 436 hertz, so 1 divided by that. And again, the 1 is not used for significant digits. Simply use the number you're given, decimal 0.0229 seconds. And lastly, C. What is the wavelength? So we know frequency, we know period, we know speed. So if we're looking for wavelength, we can have the universal wave equation, V equals lambda F, solve it for lambda, divided by F, so it becomes this. Frequency, you can see instead of using hertz, I use seconds to the negative 1, and of course the seconds and seconds cancel, and we're left with wavelength in meters, 0.787 meters. Okay? Number 16, if you wanted to increase the wavelength of waves in a rope, should you shake it at a higher or lower frequency? If we want to increase the wavelength, make the separation of waves larger. If we take a look here, the universal wave equation suggests that V is equal to lambda F. So if we're looking at wavelength, if I divide by F, we can see lambda. If I make V bigger, wavelength's bigger. But if I make F bigger, the overall result of this number will be smaller. So increasing frequency will lower the wavelength. Because to make this equal, if I increase this number, it's going to cause the overall wavelength to be less. Just like in math. You know, if you increase the denominator and leave the numerator the same, our number is going to get smaller and smaller overall. But if I was to make F a smaller and smaller number, if V is constant, taking that divided by a smaller number will give me a bigger number overall. So decreasing frequency, in fact, increases wavelength. Okay, so that's more of a qualitative type question by looking at the relationship. 17, what is the speed of a periodic wave disturbance that has a frequency of 3.50 hertz and a wavelength of 0.7 meters? So we know frequency, we know wavelength, we're looking for speed. Okay, so we know wavelength, we know frequency, we're looking for speed, so of course we have this relationship, V equals lambda F, lambda times F. So 0.700 meters times 3.50 hertz, or I can use the unit hertz as equivalent to seconds to the negative 1, which will make sense here. Meters times seconds to the negative 1 is simply meters per second. So I get 2.45 meters per second. 18, how does increasing the wavelength by 50% affect the frequency of a wave on a rope? So again, another qualitative type question there, folks. If I think of it like this, so I have a wave here, and if I increase it by 50%, what's 50% of 2? 1. So add 1, I get 3. So if I'm going from 2 to 3, 3 divided by 2, 1.5 times greater. Okay? So let's take a look here. So if I have a wavelength, now if I divide it into sections as you see here, okay? One wavelength is 2. To make it 1.5 times bigger, you can see what I did here. I need to extend this part so that it's over here. So if I do that, Increase in the wavelength means decreasing how many complete cycles per second. So here we see a complete cycle only takes this much time. Now a complete second takes this much time. So if the wavelength becomes 1.5 times or 3/2 times greater, frequency becomes 1 over that. Or 1 over that is simply 2/3 times as great. So that's a tricky question. There a little bit of math manipulation. Diagram helps. But you can see that 1.5 times bigger, and it becomes, the frequency is 2/3 times as great. Next, number 19. The speed of a transverse wave in a string is 15.0 meters per second. If a source produces a disturbance that has a frequency of that, what's the wavelength? So here we have speed, frequency, what's wavelength? So I think universal wave equation again there, folks. V, F, we're looking for lambda. So V equals lambda times F. If I'm solving for lambda, divide each side by F, and you can see what the rearranged equation looks like. 15 meters per second divided by 6.00 seconds to the -1. Seconds cancel, I'm left with meters. 20. How many questions we have? Or 25, I'm going to omit 24. 5 wavelengths are generated every 0.100 seconds in a tank of water. What is the speed of the wave if the wavelength of the surface wave if it was 1.20 centimeters? So I make a note here, change to meters, because all of these equations imply that we're using seconds as time, meters as distance, so we need to change that to meters. So we know 5 length, we know the period, we know, now the 5 wavelengths, that's really 5 cycles. How many cycles per second? Oh, wait a second. Yes, we have cycles and the time period in which those cycles are. So that'll help us figure out frequency if we need, because remember, frequency is cycles per second, and we're given how many cycles or wavelengths. Complete wavelengths is a cycle per second. So let's take a look there. Number 20. So 20, yes, frequency, we have to figure that out first. We know there's 5 complete waves, and that happens at 0.100 seconds, so that's 50.0 waves per second, or 50.0 hertz. Now notice this 5 here does not come into play with sig figs, because it's an exact number. We're only using measured quantities. And then what else are we told here? So we know frequency, and we're looking for what is the speed. If we know frequency, we know wavelength, I think we can figure out speed then. So there we have it there, folks. We know what frequency is. We know what the wavelength was when we changed it to meter sticks, because it was originally 1.20 centimeters, 0.600 meters per second. 21. If we look here, let's wait for the announcement to finish.
Dakota Spadu, come to the office, please. Nathaniel Bennett. Andrew Mares, Logan Mitchell, Darian Leary,
take a look.
and Dakota Spadu.
A periodic longitudinal wave that has a frequency of 20 hertz travels along a spring toy. If the distance between compressions is that, what is the speed of the wave? So if we take a look at that, what do you mean by compressions? Well, here it's a longitudinal wave, so there's compressions and expansions, or rarefactions. So we know the frequency, the distance between compressions, so compression, expansion, compression. So that's a wavelength. So really, that 0.600 meters is a wavelength, the distance between corresponding parts. So we know wavelength, we know frequency, what's the speed? So again, universal wave equation there, folks. We know frequency, so it's just kind of interpreting. Do we know wavelength? Do we know frequency, etc.? So 0.600 meters times 20 hertz, or representing it as 20 seconds to the -1, 12.0 meters per second. All right, getting near the home stretch here, folks. After we're done this, you should be able to easily do the assignment. How does the frequency of a wave change when the period of the wave is doubled? Okay, so another one of those qualitative questions. Since f is equal to 1 over t, and if t is becoming 2 times bigger, the overall effect here is 1 over 2, or half times as great. Okay, so just simply manipulating the relationship there, and we get the answer. 23, describe the change in the wavelength of a wave when the period is reduced by 1/2. So it's 1/2 times as great. Again, we can take a manipulation here, folks. We know V is equal to lambda F, or the other way of representing the universal wave equation, V is equal to lambda times 1 over T. So if I take a look here, I'm going to just rearrange this for lambda. So multiply by T, lambda is equal to V times T. So if period becomes 1/2 as great, the overall effect is 1/2 as great. So lambda becomes half as great by looking at what happens to that equation there. And then putting in a factor there and seeing what the result would be. Okay, last question. Last question, a nice question that would show up on a quiz. We're going to skip 25. A hiker shouts toward a cliff as shown. The echo is heard 2.75 seconds later. So that is the time to go there and back. Okay? So the question is, what is the speed of sound of the hiker's voice in the air? And the wavelength of the sound is 0.75 meters. What's the frequency? What's the period? All right? Okay. Hopefully that's the last interruption. So if we take a look here, folks. Take a look. So that's there and back. Don't forget that echo, the time to hear an echo later, is there and back. And we know the separation between the hiker and the cliff is 465 meters. So you'll see that these do not correspond with each other. To make them correspond, I either have to take half of the time or double the distance. So as I say here, that must correspond to the same scenario. So I think what I did there is I just divided the time by a half. If it's 2.75 seconds there and back, then just simply in one direction, we take that divided by 2, we get 1.38 seconds. Okay? So that's the trick with this question here. So time to cover a distance of 465 meters is just simply the time there and back divided by 2. So that's easy. To figure out the speed, it's this distance divided by time, 465 divided by 1.38, 337 meters per second. And then that's the tough part of the question. Once you're done that, it's easy. Figure out the wavelength is 0.75. What's the frequency? So once I know speed, it all comes together now. So I know wavelength. I'm looking for frequency. I know speed from the previous question. So let's rearrange this for F divided by lambda. Divided by lambda, I get this, which is 449 seconds to the -1, or 449 hertz. The next question was, what's the period? If I know frequency, T is equal to 1 over F. So that gives me 1 over 449. So that is 0.00223 seconds. And I did actually do number 24 here, but I think it's very similar to these other ones in which we're kind of manipulating the equation. So I think what I'll do is I'll call it quits there. And you should be able to, folks, you should be able to have everything that you need to answer the first part here, the qualitative part of wave properties, and then all the calculations. If you have all those formulas on one piece of paper, it makes it really easy to refer back to. All right. So you can work on this assignment now, and we'll see you again.